Okay, so let us start. This course is second year applied mathematics for the second semester. The course name is numerical analysis. The course code is AMM 204G2. So from last year we were teaching this course AMM 204G2, but before that we call it as AMM 221 GE2 with the same name, right? So if you want to look at the past papers for the previous years, the year before the last one, you may need to look at the past papers for AMM 221 GE2, right? So it's the same course, almost same, but slightly modified according to the new syllabus structure, right? And the course code names are renamed with the new numbers, right? So this time we are teaching it as AMM 204. Right? So in this course, we basically teach you some basic concepts of numerical analysis, right? Where what are the materials you need to know to do some numerical computations and stuff like that, right? So starting from the basic computer arithmetic. Right, so this is a 2 credit course, and as usual, you will have 4 questions in the final paper, and you are supposed to answer 3 questions, right? So as of now, the faculty does not have any decision made on when to call the students back and how to conduct the exams and things like that. So as of now, we will be continue doing this teaching online, right? So once the faculty decided its policy on examinations and other materials, other related stuff, then we will let you know how we are going to conduct the ICAs of this course and how the evaluation is being done for this course, right? So that depends on how the faculty decides, right? So up to that point, what we are going to do is to, according to your regular timetable, we will continue teaching this numerical analysis via online, right? So your timetable is uploaded in the dean's office website. So I share what are the times I am going to teach this course in your WhatsApp group yesterday. Today 12, and I believe Thursday 9 o'clock or 10 o'clock time is what is allocated for us. And then Wednesday 8 o'clock classes, we will be teaching alternatively. So this Wednesday, that means tomorrow 8 o'clock, I will teach the class, and then next Wednesday the other applied teacher will teach the course, and then we will come back to the other Wednesday. So on the odd weeks, the numerical analysis, and the even weeks, you will have the other applied mathematics course, right? So those are the informations regarding the course, right? The timetable and everything. As usual, we will share the Zoom link on the WhatsApp group, and we will post the lecture notes once every week of lectures are completed on the LMS, right? So those lecture notes might be slightly different from what we are teaching here, because those are the lecture notes from a previous student, right? Scanned and uploaded. So you need to be aware that there might be some mistakes in that lecture note. So you need to be careful about those, right? So because that's a student's notes which is scanned and posted, which will be scanned and posted, right? So, and for the people who has trouble with the internet, I know there is a problem all over the country with the internet and the flood and everything. So in case if you miss the Zoom class, you don't need to worry about it. What we are going to do now is to after 1 week of lectures is over, we will post the videos in a YouTube, right? And we will share the link for those YouTube videos with you on the WhatsApp group, so you can take a look at those the YouTube videos at your convenient time, and study based on those videos as well, right? So even if your internet is broken down, or even if you could not follow the lectures on time on Zoom, you don't need to worry about that. You can always take a look on those lecture videos on YouTube once the lectures are over, right? So that link for the YouTube will be shared with you on the WhatsApp group once the videos are uploaded. And so that is how this lectures will be conducted. Right. So now we will get into the course. So this course has 4 main subjects. First one is computer arithmetic. Second one is fixed the location of zeros. Third one is interpolation, and fourth one is numerical integration. So first chapter is computer arithmetic. Computer arithmetic. So here, what we are basically going to look at is how computers are handling numbers, right? So right, so we are going to see how numbers are handled inside a computer when the computations are done using a computer, right? So first one is we will see. Right, so first we are going to see polynomial representation of a number, right? Right, so we are going to see the polynomial representation of a number, right? Say for example, this is something very familiar for you, right? You have seen this many times, right, in your life from very basic mathematics courses, right? Say for example, if you look at this number, right, 3456, right? So obviously when we give a number, you know it is a base 10 number, right? So you know there are different bases. You already know base 10 is the commonly used base, right? But you have base 2, base 4, base 8, and base 16 as well, right? So if you have a number like this, right, so you can actually write this in this fashion, which you all know, right? So 3000 plus 400 plus 50 plus 6, right? So that's an obvious representation of this number, right? So thousands, hundreds, tens, and 10 to the power 0th powers, right? So constants, right? So that's how you can represent a number, right? Base 10 number. So in particular, you can represent this as follows, right? So 3 times 10 to the power 3 plus 4 times 10 to the power 2 plus 5 times 10 to the power 1 plus 6 times 10 to the power 0, right? So if I give you a number like this, 3, 4, 5, 6, right? 3456, then you can write this as 3 times 10 to the power 3 plus 4 times 10 to the power 2 plus 5 times 10 to the power 1 and 6 times 10 to the power 0. So you can see that this base 10 number, right, is represented as a polynomial in 10, right? So this is a polynomial, right? So this is something like this, right? So a naught to the power 10 to the power some alpha 1 plus a1 10 to the power some alpha 2 plus a3 times 10 to the power some alpha 3 and so on, right? So you are representing a number like this, a polynomial representation of a number, right? So this can be done for any number and any base, right? So if you, for example, if you have 1011 base 2 number, right? So you studied about base 2 at very young age, right? So in O levels, you know that. So this is basically, right? So 1 into 2 to the power 3 plus 0 into 2 squared plus 1 into 2 to the power 1 plus 1 into 2 to the power 0, right? So this is a polynomial representation of a base 2 number in 2, right? Polynomial in 2, right? Similarly, you can write a base 4 number, you can write a base 8 number or any number. You can give a polynomial representation. So in this way, what I am going to do is I am going to generalize this, right? For a common base, one arbitrary base, I am going to give a number in its polynomial representation, right? Okay, so any number on a given base B, right, can be represented as a polynomial, right? So this is the first concept, right? So you can write down a number on base B in a polynomial representation, right? So with starting with some degree n all the way up to degree 0, right? So these coefficients a naught, a1, an, they will satisfy certain condition. One of them is those coefficients are in between 0 and the base, right? Say for example, if it is a base 10 number, you know that these digits 3, 4, 5, 6, all of them can be numbers between 0 and 9, right? So that is how you represent a base 10 number, right? So base 2, you know, only 0 and 1 you can use because that is how you represent base 2 numbers. So the coefficients are always between 0 and 1. So similarly, if the base is b, then you can represent this as the polynomial representation with the coefficients are the numbers between or digits between 0 and b minus 1, right? So this is a general representation of a number, a real number, right, which is represented as a polynomial. So now what we are going to do is to, because any number on any base can be represented as a polynomial, right, we are going to use this polynomial representation to study the arithmetic which is being done inside a computer, right? So instead of looking at numbers like this, we will see the equivalent polynomial representation, and we will try to study the computer arithmetic based on those polynomial representations. So in order to do that, we have to see how to handle polynomials first, right? Because when you see how to handle polynomials, then only it is useful, right? So to study the rest. So let us see the concept called nested form of a polynomial, right? So now I am going to consider an arbitrary polynomial, right? Right, so let us consider a polynomial like this, right? So now if you want to evaluate a polynomial at a number, right? Right, so if I want to evaluate the polynomial at alpha, right, alpha be a number, right? So alpha can be 1, alpha can be 5, alpha can be minus 10, alpha can be minus 1000, whatever it is, right? So if I want to evaluate this polynomial at a point, right, then I know that I substitute x equal to alpha in the polynomial to evaluate, right? So if I want to evaluate at 2, you know, I have to put x equal to 2 to evaluate, right? So that is the basic thing which you all know, right? So let us say the evaluation, right? So let's see an example. Okay, so let us evaluate x equal to 1, this polynomial at x equal to 1, right? So I'm going to explain this example in two different ways, right? Evaluation in two different ways. Just to tell you how the nested form works and how the regular evaluation works, right? So regular evaluation, you all know this, right? So I divide this into two pieces, right? So obviously, you know, you want to find P of 1, right? So that is what you want to get. So you get 1 cubed plus 2 times 1 squared minus 1 plus 1. So you can simply evaluate this, right? 1, 2, 3 minus 1 plus 1, so 3. So this is simple, right? So this look very simple. You just substitute 1 and you get this, right? So now what I am going to do is I am going to see this px in a nested form, right? So here I am going to see nested form. So what I am going to do is I am trying to factor, right? So I am going to factor like this. So let me show you how to do this. And so first what I do is this, right? So you have this x cube plus 2x squared, sorry, minus x plus 1. So I am going to do this x times x squared plus 2x minus 1 plus 1. Right, so I factor x from the first 3 terms. Next, what I do is I take x and then another factoring. So x plus 2 minus 1 plus 1. You have to be careful with the brackets, right? So when you're doing the factoring, right? So you have to be careful with the brackets. So now you can see that I have factored in a way such that, right, I eliminate powers, right? So x to the power 3 I eliminated, x to the power 2 I eliminated, right? So when I write this in the nested form, this is called the nested form. When I write this in a nested form, right, you can see that I have eliminated the factors, right? So the power part I eliminated, right? So now if I want to compute this, you can see that I have to put 1 times 1 times 1 plus 2 minus 1 plus 1. So I have to start from within the small bracket. So 3 minus 1 is 2. 3 times 1 is 1 times 3 is 2. 2 times 1 is 1 plus 1 is 3. Right? So both ways I get same answer. Right? That is fine. Okay. But so this is a simple example. Right? So why I have to go from this form to this form? What is the differences, right? So in which way the computation is different, right? So this will tell you why studying the computer arithmetic is important, right? So what I'm going to do is I'm going to count. So this is called operation count, right? So I'm going to count operations, right? So I'm going to count the operations. So operations means multiplication, addition, right? So right, so multiplications and additions are called operations. So then you will see what is dividing, right? Multiplication is operation. So what is division? Division is also a multiplication, right? Because if you divide something by 2, means you multiply that number by 1/2, right? So if you have a division, you count that as a multiplication. So multiplication includes division as well, right? So multiplication includes division as well. Similarly, if I say addition, subtraction also comes under addition. So plus and minus are considered as addition. Dot or division is considered as multiplication. So if I want to count the operations, I count the number of multiplications and additions in this process, right? So that is what I'm going to check, right? So here, one thing is important here. First of all, when I try to compute multiplication, I have to recall you that here you have 1x, right? If I say x, it is 1 times x, right? So first I will count the multiplications, right? What are the multiplications I have? 1 times 1, I have 1 multiplication, right? So 1 times 1 is a multiplication. So I have 1 multiplication there. Here, 1 squared, right? In 1 squared, you have a multiplication. So that is another multiplication, correct? And then 1 squared multiplied by 2, there is one more multiplication, right? So 2 dot 1 squared gives you 1 multiplication, right? And then 1 cubed, right? So 1 cubed, you already have 1 squared. So computer will compute 1 cubed, right? So in 1 cube, you know you have 1 squared. So actually it is 1 times 1 squared. So that will count this as a multiplication, right? So there are 4 multiplications. And so when you add up all the multiplications, you can see that there are 4 multiplications, right? Now, additions. How many additions are there? This is simple. 1, 2, 3 additions are there. Right? 3 additions and 4 multiplications are there. Now in here, in this process, how many multiplications and additions? Right? Multiplication, you have a multiplication here, right? So 1 dot 1 plus 2 is a multiplication, right? So you see that there is 1 multiplication. And then there is another multiplication here, right? Another 1 dot 1 plus 2 minus 1. So this is the second multiplication. There are no other multiplications, right? Here is a multiplication and then here is a multiplication. Only 2 multiplications, right? So you have only 2 multiplications. Additions, you can see 1, 2, 3 additions, right? So if you compare both ways, you calculated the same thing. You evaluate the polynomial at 1, right? If you evaluate directly by the regular method which you all use, which we all use, right? Which we study in our O-level maths or somewhere, right? So in this process, you can see that you have 4 multiplications, right? There are 4 multiplications. But in the nested form, you see there are 2 multiplications. Additions are same, right? 3 and 3. So in this process, you can see that if you do go through the nested form, right? This is just a 3rd degree polynomial, right? X to the power 3 is the biggest power. Even for that, you can see that there is a big drop in the number of multiplications required. So especially in a computer arithmetic, multiplication takes long time than other operations, right? So if we reduce the number of multiplication, then that is good for us. It will make the computation time less. So you get the computer giving the answer fast. So always in computer programming, they will try to reduce the operation count. Right? So let me write it down. Okay, so this reduces the operation count so that the computation becomes faster. Right, so this example show you that the nested form is quite useful here. Right. So now developing up this nested form, right? So we try to see the polynomial evaluation in a different way, right? So that is called Horner's algorithm. Right, so Horner's algorithm, right? So Horner's algorithm is a mechanism which is used to evaluate the polynomial, right? So that is basically this algorithm basically helps you to evaluate a polynomial in a nested form, right? Say, for example, instead of calculating 1 cube plus 2 times 1 squared plus 1 time minus 1 times 1 plus 1 and sum all of them to get the number, this Horner's algorithm, what it would do is, right, so it would take x plus 2, right, and so 1 plus 2 and multiplied it by 1 and then subtract 1 and then multiply again by 1 and then subtract and add 1, right? So that is the process the Horner's algorithm is basically going to do, right? So it will calculate first 1 plus 2 and then 1 times 1 plus 2 and then that minus 1 and then that value times 1 and then that value plus 1. So in that way it will continuously compute, right? So for example, this is how it is going to do 1 plus 1 and then, so this, if I say this is some k naught, right, then k1 is 1 times k naught and then k2 is k1 minus 1, right, and then k3 is 1 times k2 and k4 is k3 plus 1, like that it will do, right? So 1 plus 1 and then 1 times this, so 1 plus 2, no, right? So in this example, this is how you can, if you want to go through an algorithm, this is how you can do. First you calculate this and you multiply that with 1 and then you subtract 1 from that and then you multiply that with 1 and then you add 1, right? So step by step, if you want to compute, if you want to write a program, this is what you do, right? So first step you do this, second step you do this, third step you do this, so on. So this will be the thing, right? So answer is, the final answer is k4. Whatever you get for k4 will give you the final answer, and that is 3. Right? So that is how originally we do. Right? So here also in Horner's algorithm, we are going to follow a similar type of approach to evaluate a polynomial. Right? So let me write it down in a general form. So x to the power naught, I can avoid writing x to the power naught, right? So you all know that. So an minus 1x plus an. Right, so this be the polynomial, right? So right? Suppose you want to evaluate this polynomial at some x equal to t, right? So you want to evaluate this, right? So okay, so to get, right? So to get this value Pn at t, we will apply the Horner's algorithm. So what is the Horner's algorithm, right? So let me write it down. Right, so if you apply the algorithm in this fashion, right, so you set b naught is equal to a naught, right, the first number as same, right, and then you start finding b1 b2 b3 up to bn, right, b naught you fixed and b1 b2 b3 up to bn by using the previous b and the corresponding a, right, the coefficient of a. So if you do that, you will get some numbers b naught, b1, b2, b3 up to bn. So in that case, right, we what we get as bn is the evaluation of the polynomial at t, right? But interestingly, in addition to that, right, but interestingly, you get more than that, right? In addition to this, right, what you get is you get Pnx is x minus t times P of n minus 1 times x plus r of n, right? So you get that as well. So this means you reduce the polynomial Pn of x in this, right? So here you see that it is basically a polynomial division, right? So this means when you divide the polynomial by x minus t, right, then what you get is you get a quotient that is Pn minus 1, right? So 1 degree less polynomial, right? So you know when you divide x to the power n by x, you get x to the power n minus 1. So that is 1 degree less polynomial, and also you get remainder Rn. Right? So we can prove this. Right? So proof is not a big thing. So you know that Pn of x is a naught x to the power n plus a1 x to the power n minus 1 plus all the way up to a n minus 1 x plus a n, right? But from this, right, so from this you can see that ak is bk minus t times bk minus 1, right? Ak is bk minus t times bk minus 1, but a naught is b naught, right? So a naught is b naught, so that is b naught times x to the power n plus a1 is b1 minus t times b naught, right? According to this, b1 minus t times b naught x to the power n minus 1, right? And all the way up to a n minus 1 is b n minus 1 minus t times b n minus 2 x plus a n is b n minus t times b n minus 1. And so you have this. Right? So now you can combine the like terms, right? So there is a b naught and there is another b naught, right? So you take this and combine together, this and this combine together, this and this combine together. Like that you can take out the terms and combine them together, right? So the rest I leave as an exercise, right? From this you will get this x minus t times b naught x to the power n minus 1 plus b1 x to the power n minus 2 plus all the way up to bn minus 1 plus bn. Right? So you will get this, right? So this is just a simple mechanical work which you can do, and when you simplify, you get this, right? So that is basically this, right? So that's x minus t times pn minus 1x plus, because bn is Rn, right? So you know that bn is Rn, right? So you get this, right? And when you put x equal to t, right, clearly pn of t is t minus t times pn minus 1t plus Rn. So this is 0, so it is clearly Rn. Right? So you can easily see these two. Right? So this is how the Horner's algorithm works to give you an evaluation of the polynomial at some point, and in addition to that, it works as a division algorithm as well, right? So eventually it does not, it's not only evaluating the polynomial, right, but it also helps you to apply the division algorithm as well, right? So this is how the Horner's algorithm works. Right. So now what we are going to do is to next class, right? So we are almost in time. So in the next class, what we are going to do is we are going to continue doing this Horner's algorithm. Right. So I started with the n degree polynomial, right? I ended up with n minus 1 degree. If I apply again Horner's algorithm to that, I will get n minus 2 degree. One more time, I will get n minus 3 degree, right? So in that way, I can apply until I get a constant, right? So in that way, I continue applying Horner's algorithm again and again and again for the quotient polynomial until I get a constant value, right? So once I do that, it will help me to get to a expansion called Taylor's expansion. Usually, in Taylor's expansion, you have to differentiate the polynomial. Right? So if you apply Horner's algorithm continuously, you can get the Taylor's polynomial without doing the differentiation of the polynomial, right? So we will talk about that in tomorrow's class. We will see again on tomorrow morning, 8 o'clock. Right? So I'm stopping here, and the rest will be continued on tomorrow.